Yeah, good evening. So welcome to today's session. Just a minute. So in today's session, we'll spend some time on the regression, where as discussed in the previous class, we'll take one problem and see how to solve, how to find the regression line corresponding to the given data. Then we'll have some introduction related to ANOVA. Then, if possible, we'll try to solve or discuss one-way ANOVA problem, and continue with the two-way ANOVA problem. So, am I audible? Like, can you confirm so that we'll proceed? Yeah. Okay. Thank you. Now, simple mathematical way of doing the thing. Suppose some data is given like this, where so x, the independent variable, is given, and y, the dependent variable, is given, right? And so we need to find the relation between x and y, where here x is the independent variable, x is the independent variable, and y is the variable which depends on x. And here, as discussed in the previous session, so here the requirement is to go for a linear regression, y equal to beta naught plus beta 1x. Straight away, so we are going for a relation between x and y, where x is the independent variable, y is a variable which depends on x. So otherwise, as discussed earlier, first we need to see whether these two are related or not. That is very important when we proceed further, right? If both the variables are related, then it makes sense us for to go ahead and try for regression of either type, either it may be linear regression or the non-linear regression. Right? So that is it. That is the first thing in general. What we have to do is first we need to find the relation, whether the relation exists between the two variables or not. If yes, then it makes sense that we proceed further and try to find the type of relation or the type of regression which what we require or what we want to have between the two variables. So in this case, it is straight away given. So where we have to find the regression line of the type y equal to beta naught plus beta 1x. That is a simple linear regression. Now, as discussed in the previous sessions, if y equal to beta naught and plus beta 1x is the linear regression which we are trying to have, then immediately we know we have these two equations called as normal equations. So very simple, as discussed in the last class also. So where we have summation y, beta naught into summation n, beta 1 into summation x. So next one, because if we are differentiating with respect to beta 1, therefore x comes, that is like derivative of 2x square if we do, or derivative of ax we do, what we will get is into a, right? Like this, when we differentiate the beta 1x, when we differentiate the error function with respect to beta 1, then we'll get x, therefore we'll get into x. So that is the reason we get this, right? Summation xy, beta naught into summation x, beta 1 into summation x square. So very simple. So just whatever the variables are, now already we have the data with respect to x as well as y, and what we require is the summation x, summation y, summation x square as well as summation xy. Right? So very simple to do these calculations. Right? So x, y, x square, x, y, and summing the corresponding values what we require. Summation x, summation y, summation x square, summation x, y, etc. So once we had these values, then very simple. So we'll plug in the values in the normal equation. So summation y value beta naught n is the number of data points given. Here in this case it is 6. I think 1, 2, 3, 4, 5, 6. Yeah. So n 6 points are given, 6 into beta naught and beta 1 into summation x and summation xy, beta naught into summation x, beta 1 into summation x square. So now we know it's very simple to solve. If we solve these two equations, we will get beta naught as well as beta 1 value. That means in turn we get the equation of the linear regression, the equation of the linear regression where y is dependent variable, x is independent variable. So how to solve these equations? I assume that we are all familiar with respect to this. How to solve the equations? Very easy. I think very simple. I assume that we are all aware of this. That's why I couldn't explain this. Very simple here, multiplying. Otherwise, if you are not able to recall, so multiplying this by 177 and multiplying this by 6, then what happens? The beta naught coefficients become the same. Right? So multiplying this by 177 right, throughout the complete equation, and multiplying this equation throughout by 6. Then what happens when we subtract here, because 6 into 177, 177 into 6, if we subtract, this gets cancelled, right? This goes. So then what we'll have is 177 into beta 1, 6 into 5387, both contains beta 1. From that, if we simplify this, then from which we'll get beta 1 value. Once we had a beta 1 value, if we substitute beta 1 in any one of the equations, we'll get beta naught. So very simple, because we had a calculator. Mostly we are doing by using calculator. That's why even though numbers are very larger, it may not be a difficult thing to do. So once we had beta naught and beta 1, then in turn, so this is the equation which fits into the data what we had. So this is the optimal possibility which minimizes the error which we have been discussing when we try to fit a regression equation or regression line or regression curve into the data what we are trying to have. So I hope that is clear, this example. So any doubts if you had with respect to this, let me know, then we'll discuss, otherwise we'll proceed further. Initially we have to find there is a relation or not, then only we go for regression. How we found there is a relation? Here in this case, actually clearly they mentioned that we need to go for. So fit a regression line. That is what in general, if suppose we when we really work with respect to real-time data, so where we had such kinds of things, then we'll try to establish whether these two are having any relation or not. If yes, then we take it further, then try to go for this regression, right? So that's why as explained. So here just they are asking us to find the regression line of this form which fits into the data. That's what we are doing. Otherwise, really, if this data is given, first thing when we work with the modeling of the data and we try to have the linear regression or regression of any kind, multilinear regression or non-linear regression, that is regression of any kind. So first what we do is we'll try to find out, is it worth going ahead and trying for a relation or not. So where we'll try to find the coefficient of correlation. So based on that, so we'll try to proceed further and try for this approach. Yeah. So that's why here we didn't try for that. So otherwise, in reality, when we try with modeling of a data in a real sense, we have to we try to establish the fact whether these two variables are related or not. If yes, then only we proceed further. Okay. Yeah, then okay. I hope that is clear. So this is a simple solving of equation. Even actually nowadays it is not a big challenge with respect to solving equations. So in calc itself, up to 2-3 variables we can solve with the help of calculator. But better to know the procedure. So is it fine? Whether voice is clear? No, actually, those who are really work with this kind of stuff, what I suggest is you can practice actually. You can practice, take some data sets. Maybe you can download it from the Google, or so now the government of India is there is one government of India website where we can have the data sets, the real data sets of various departments. Right? So if you can play with the data, right? So you can take some data sets and you can try to find the linear regression or the polynomial regression of any kind. Okay. So here voice is breaking. 1 minute. Just a minute. But no, I think. So government of India website I will share. I couldn't remember exactly. I think I'll share the website where you will find the real data with various government departments where you can you can take some of the data sets and you can try to play with some models. Particularly, this is one of the important good model, right? And here don't get yourself feeling some uncomfortable with respect to the tool. Like even you can take Excel by using Excel also we can try to have linear regression or the regression of any kind. Or if you are comfortable with R, yes. If you are comfortable with Python, you can do it. Let's try to see how it works. What are the theory we discussed in the class, and how to correlate the theory with respect to the implementation. Next, after once we complete makeup examination, we'll start looking towards the implementation also. The Government of India website I will share. So then we'll take it further. The another the form which we use or which represent mathematically the regression line, regression equation of y on x is can be written as this is our regular equation of a straight line. If you remember the geometry what we learned in the initial days, so that is the equation of a straight line y minus y1 equal to m into x minus x1, where m is slope of the straight line. This similar lines here, the regression equation of y on x is y minus y bar into rxy, which plays the role of a slope into x minus x bar. This is another form of the regression equation, where y bar is mean of y and x bar is mean of x, where rxy, which is similar to the slope of a straight line, is called as it is a regression coefficient of y on x. So which which we can have, which we can find with the help of sigma xy by sigma x square. If you remember, what is this? This is nothing but our covariance. So covariance of xy, and this is variance of x. This is covariance of, that is summation x minus x bar into y minus y bar is the covariance of x and y. And similarly this. This is one form of the regression equation. And here if we see from this, we can say always the regression line passes through the point x bar and y bar, or the point x bar and y bar, the point x bar comma y bar, where x bar is mean of x, y bar is mean of y, always lies on the regression line or regression equation. That is one observation what we can say. So next, actually this is one of the good topics. As requested in the previous class, we will try to have some discussion, then we will continue it further in the next class also, those who miss. So what is this analysis of variance or ANOVA? So in where we need to use this. So now that's one example which I took from some of the websites. Right. Suppose the two models are there. Right. Two models are there, and we want to find whether the mileage of these two models are different or same. That is simply what I say is, if I say take this as first model as the first population and second model as second population, and the average mileage of this model and average mileage of this model are same or different. That is what we want to check. That is mu1 equal to mu2, right? We want to verify whether mu1 equal to mu2. This is the hypothesis or the claim we want to verify in this context. Right? Okay. Now the question here is it possible for us to do this, solve this problem now? Or how, if so, how to do it? Or whether we know how to solve the problem of this kind. So I hope that this is clear, right? So two populations are there, and we say we want to find whether the mean of the means of two populations are the same or different is the one which we want to validate. Is it possible to do it now? Or whether we need any other topic or the concept to answer the question? Is it possible to answer this question or not, or whether we need to go further with some other topic to solve this? If yes, how to do it? Yeah, testing of hypothesis already what we had covered. Perfect. So testing of hypothesis related to means problem, right? Two means problem. So depending on the size of the sample, we go for either Z distribution or T distribution, right? So mostly it is T distribution depending on the size, right? Because here in the case of number of cars, you can't have many cars in the sample. So you may have 10 cars or 5 cars, 8 cars in the sample where we try to find the mileage, right? So if it is a small sample, then we have to go for T distribution, right? T distribution helps us to understand that is the relation between the populations means when we have two populations. Yeah, we need mileage data. That is, we have to go. That's where I did. This is one population. This is another population. So where we want to establish whether mu1 equal to mu2 or not. Again, it's the alternative hypothesis. Mu1 is not equal to mu2. Then what we do is we will select one sample related to this population, another sample related to this population. Then we will have the mean of the population. That is average mileage with respect to this we get. the standard deviation. Similarly here, by using the sampling data, we try to validate this hypothesis, right? So depending on the sample size, we go for either Z distribution or T distribution. Mostly, I think the sample size is going to be simple. We will go with T distribution, or we go for Z distribution, right? So I think we can do it. So suppose if it is something like this. Suppose here in this case, a salesman wants to find whether the mileage of these three models are the same or different. Then what to do? So that means here we have population 1, population 2, and population 3. So population 1, population 2, and population 3. And what is the hypothesis of the claim we are going to validate or verify? It is the average mileage related to all the three models, right? That is mu1 equal to mu2. So mu1 equal to mu2 equal to mu3 is the claim we have to validate. So how to do this? Any idea? Any guess? Whether we need to go with some other topic, whether the already a familiar topic or the familiar concept can be used to answer this type of situations. Any idea like whether we can use any of the procedure already established to validate this mu1 equal to mu2 equal to mu3 against mu1 not equal to mu2 not equal to mu3? Any idea left? Yeah, we worked only with the 2-min problem. But one idea I am getting is, so what I do is 2-min problem I know, right? I'll go with this, right? First I'll take these two, right? I'll go with this. So here I'll go with this, and that is 2-min problem, right? Mu1 equal to mu2 I validate, mu2 equal to mu3 I validate. That is another 2-min problem, and third one is I go for mu3 and mu1. Whether it makes sense or not. And here one answer or one query that I had is, is it possible for us to go ahead with a chi-square in this case? So the chi-square is a valid concept that we can use to answer this. If yes, why, or if not, why? Chi-square is yeah, perfect. That is what I have been telling most of the time for you guys like you. It's very important to identify what is the model to be used. Once it is clear, then because you are really working with the data and using various tools, and you are good in coding, etc. kind of stuff. So for you, the most important thing is identification of the perfect tool which I can use. So chi-square is chi-square we use for proportions, not for mean. That's why chi-square won't work. Chi-square is for proportions. Out of these many cars kind of situation comes, then we have to go for chi-square. Several proportion kind of discussion is there, then we have to go for chi-square distribution. So chi-square won't work. So one idea is some of you also responded saying that. So we can go with mu1, mu2. That is 2-min problem which we can do. Mu2 and mu3 again 2-min problem we can do. Mu3 and mu1 again 2-min problem we can do. Yes, we can do it. But here, if it is 4 populations, it doesn't make sense, right? Doing this, right? And that too, but the transitive property. Whether we can validate for the kind of sequences A to B, B to C, A to C is fine. Whether A to B, B to C, C to D, then whether we can say A to D and also we can come out with conclusions. No. At least up to this, okay, at least we can try with A to B one combination, yes, B to C another combination, then A to C another combination, then at least we can come out and say some conclusion, right? But if we continue this with 4 populations, then it doesn't make any sense. Okay? So then the alternate or then the approach what helps us is the ANOVA problem, the analysis of variance. Even though say analysis of variance, but here we are not going to test the variance again. Here we are going to test the population means, where we will take the help of variances. I repeat here, it is not that we are going to test the variances, right? Variances, now if you remember, where first we had discussion with respect to means, mean of one population, mean of 2 populations, like this. Next we had proportions, mean of 1 proportion, mean of 2 proportions. Right? But here maybe name indicates analysis of variance. It is not that we are going to validate variances. Here we are going to validate a hypothesis related to means, where we are taking the help of variances. So that's why it is called as analysis of variance. Sometimes it may mislead. Yeah, I'm not saying it won't work. So I'm saying whether we can continue with mu4, mu5, right? Here only 3 populations, right? And if you see the amount of work we have to do it, mu1, mu2, that is 3, 2 means 2 populations problems, 3 problems we have to validate, 3 combinations we have to validate in this. I'm not saying it is not valid. What I'm saying is, if I had 4 populations, if 4 populations, then we can't do it. If mu is 4 or 5, then what would we use? That is what we are going to discuss, the analysis of variance. Something like this. One example I took from one of the textbooks. So some strategies are there. Whether all works or what is the whether all are having equal impact, strategy is fine. Suppose some kind of analysis if you want to do, so then what to do? So such kinds of scenarios, then we have to go for the analysis of variance concept, which we are going to discuss. So some other example, effectiveness of different promotional activities. Then quality of the product produced by different manufacturers with respect to one attribute, and yield of crop due to varieties of seeds, fertilizers, and quality of soil, etc. Suppose in this first case, if you take this, we had various types of promotional activities. So maybe it is so TV advertisement, digital marketing, or the advertisement, promotional activities through newspapers. So now we want to see how effective they are. That is, whether all the 3 are having equally effective or not. That is mu1 equal to mu2 equal to mu3. Or equal to mu4 kind of hypothesis if we want to validate. So then it comes analysis of variance. So what to do in ANOVA? The same what we. So here in ANOVA, here we what I have mentioned, we will take the help of variances. With the help of variances, we will validate the hypothesis. And in the variances and also the test, like what we have been discussing, T distribution, chi-square distribution, Z distribution. Then here, when we deal with variances, we have to go for the F test or F distribution. So this is another new distribution we are having now. F test or F distribution. So whenever we deal with the variances, then F test or F distribution is the one which we have to use. So variances here, we'll see how to do it. So two types of analysis we do, two kinds of variances we use. One is the within the groups. Right? So within the groups, how the variances happens, right? How it differs, how the variability happens, etc. So individually we'll see. Other one is the variances between groups. Suppose like what we had is there three products, right? First population, second population, third population. Right? That is first group, second group, third group. So within the group means in every group we'll try to find the variances. Second one is between the group variances also we calculate. Some kinds of variances we need to complete numerical understanding here. Okay. So in null hypothesis, always this here. So means there is no difference in means and there is a difference in that means. So we test the null hypothesis, that is mu1 equal to mu2 equal to mu3 equal to mu4 and so on, depending on the number of populations we have. And the alternative hypothesis opposite, mu1 not equal to mu2 not equal to mu3 and so on. That is alternative hypothesis we use. Already this one here. So this is our same what we discussed, right? Null hypothesis is means are equal, means are not equal. Suppose this is so such kinds of observations, and we have population which is divided into three groups, and observations which are divided into four groups. So now we want to find whether the populations A, B, C, that is means of A, mean of B, and mean of C is same or not with respect to observations. So that is supposed to null hypothesis if we are going to validate. Then, so how to do it is some mathematical calculations we have to do, where we have, as discussed, so between and also within. So within the group we have to calculate the sum of squares, that is the variances we have to calculate, and between the groups, within the group and between the group, within the group and between the groups, that is between samples we have to do the calculations, where we have to find sum of squares treatment, sum of square errors, and total sum of squares we have to calculate, some mathematical calculations. Okay. So where corresponding degrees of freedom, so where r minus 1, that is the number of groups that we had, r is the number of groups minus 1 is the degrees of freedom corresponding to between groups, and n minus r is, n is the total number of observations and r is the number of groups that we have, that is the corresponding degrees of freedom, and the total degrees of freedom is n minus 1. So one after sum of squares we have to calculate mean squares, that is MSTR as well as MSE, just formula based approach. Once we had MSTR and MSE, we have to calculate here. This is the distribution what we are going to have. So MSTR mean square treatment and mean square error. So now, so next what we have to do is, so for a given or for a chosen level of significance, for a given or for the selected level of significance, we have to take the help of normal distribution, it is F distribution table. F distribution table we have to take. In F distribution table we have two types of degrees of, one is numerator degrees of freedom, other one is, I think I missed it to copy the table to show, then it will be very fine actually. So numerator degrees of freedom as well as denominator degrees of freedom we have. So where MSTR is numerator, right, its degrees of freedom is r minus 1, and MSE is denominator whose degrees of freedom is n minus r. So for these degrees of freedom, for at the given level of significance alpha, we have to take the value from the table, and already we had calculated a value and we need to compare it to validate the hypothesis like what we have been doing. And in this case, it is nothing like left tail, right tail kind of test in case of this distribution. So always it is a comparing with less than the calculated value is less than the tabulated value or not, or greater than that. Depending on that, we will take the decision with respect to the null hypothesis what we have. This is how the ANOVA calculations we need to do. So we'll break for 2 minutes and we'll continue the discussion.